Welcome to Future Forward, AI to AGI to ASI, the podcast where we explore not just where artificial intelligence is going, but what it means for civilization when intelligence itself becomes an industrial force. Today's episode tackles a bold idea that sits right at the edge of plausibility and provocation, the vision, most closely associated with Elon Musk, of placing data centers in space. At first hearing, the idea feels almost inevitable. As AI models grow larger, more energy-hungry, and more central to economies and governments, Earth begins to feel small. Power grids strain, communities push back against hyperscale facilities, water becomes scarce, carbon accounting becomes political, and so the question emerges almost naturally. If computation is no longer bound by geography, why should it be bound to Earth at all? Space appears to offer an elegant escape. Near constant sunlight, no neighbors to complain about heat or noise, no land constraints, no water rights, no national borders. In that framing, orbital data centers sound less like science fiction and more like the logical next step in the evolution from cloud computing to what might one day resemble a planetary nervous system. But intuition, especially in technology, is often a poor substitute for physics. To understand whether this vision makes sense, we have to step away from rhetoric and examine the problem through first principles. Not ideology, not aspiration, but thermodynamics, orbital mechanics, energy systems, reliability engineering, and economics. Because in the transition from AI to AGI and eventually ASI, the limiting factor is not intelligence itself. It is infrastructure. Let's begin with energy, because every computation, no matter how abstract, ends as heat. In space, solar energy is abundant. There is no atmosphere to attenuate sunlight, and solar irradiance is higher than anywhere on Earth's surface. This is often cited as the foundational advantage of orbital data centers. But abundance does not equal usability. Solar panels are not perfectly efficient. They degrade over time, they require structural support. And in low Earth orbit, which is where latency and launch economics are most favorable, satellites spend a significant portion of their orbit in Earth's shadow. That means energy storage is not optional, it is mandatory. When you run the numbers, a single modest hyperscale data center would require solar arrays spanning several square kilometers, along with massive battery systems or alternative storage technologies to survive eclipse periods. Every square meter adds mass. Every kilogram adds launch cost. Energy in space is plentiful, but energy density is poor, and density is what data centers live or die on. Then there is the most misunderstood aspect of all: cooling. Space is not cold in the way engineers mean cold. It is a vacuum. There is no air to carry heat away, no water to absorb it, no convection at all. Heat can only leave a system through radiation, and radiative heat transfer is brutally inefficient at the temperatures electronics operate at. To reject large amounts of heat, you need enormous radiator surfaces, which again means mass, structural complexity, and vulnerability. Ironically, Earth's atmosphere, which we often think of as a limitation, is one of the greatest thermal assets data centers have ever had. Air and water are extraordinary heat sinks. Space is not. As compute density increases, thermal management becomes harder in orbit, not easier. This single fact alone collapses many optimistic assumptions about space-based compute. Now consider launch economics. Even with dramatic reductions in cost driven by reusable rockets, launching infrastructure into orbit remains staggeringly expensive compared to building on Earth. Data centers are not lightweight. They are racks, power electronics, shielding, cabling, cooling systems, redundancy layers, and structural support. Every design decision must account for vibration, acceleration, radiation, and long-term degradation. What costs millions on Earth costs orders of magnitude more in orbit. And unlike terrestrial assets, mistakes are not fixable. That leads us to maintenance and reliability, the quiet killers of ambitious space concepts. On Earth, when a server fails, it is replaced. When a cooling pump degrades, it is serviced. When a rack design proves flawed, it is redesigned. In orbit, failure is final, or at best, extremely slow to correct. Autonomous robotic servicing remains experimental and costly. Radiation causes bit flips and material fatigue. Thermal cycling stresses joints and connections. Micrometeoroids do not care about uptime guarantees. Space systems are engineered to survive, not to scale endlessly. Hyperscale computing depends on constant replacement, rapid iteration, and aggressive optimization. These two philosophies are fundamentally at odds. Then there is latency. No matter how fast light travels, distance matters. For many AI workloads, especially inference, interaction, finance, healthcare, and control systems, milliseconds matter. Even low Earth orbit introduces delays that terrestrial fiber networks avoid. Bandwidth is constrained by spectrum availability, power limits, and atmospheric interference. Optical links help, but they are not immune to weather or alignment challenges. For Earth-based users, orbital compute is always at a disadvantage. Security and resilience introduce another layer of complexity. Orbital assets are visible, predictable, and difficult to defend. Their trajectories are known, their positions are trackable, they are exposed to debris, jamming, cyber-physical interference, and geopolitical escalation. A terrestrial data center can be hidden, hardened, replicated, and politically insulated. An orbital one cannot. So, if space is so constrained, why does the idea persist? Because the pressures on Earth are real. Data centers compete with hospitals, homes, and industries for power. They consume water in regions already facing scarcity. They concentrate digital power in specific geographies, raising questions about sovereignty and resilience. These are not trivial issues, and they demand solutions. But before we abandon the planet, it is worth recognizing how much untapped potential still exists here. Subsea data centers exploit natural cooling and geopolitical neutrality. Polar and high-latitude facilities leverage cold climates and renewable energy. Immersion cooling dramatically increases thermal efficiency. AI-specific chips reduce watts per operation. Waste heat can be reused for cities and industry. Data centers can stabilize grids rather than strain them. These approaches deliver most of the theoretical benefits of space without incurring its existential risks. That said, space-based computation is not entirely without merit. There are narrow, legitimate use cases where it makes sense. Processing satellite data in orbit, rather than transmitting raw streams back to Earth, reduces bandwidth demands. Deep space missions require onboard intelligence. Certain military or intelligence applications may prioritize isolation over efficiency. In these contexts, orbital compute is not a replacement for Earth-based infrastructure, but a specialized extension of it. So how should we interpret Elon Musk's vision? Less as a near-term engineering plan and more as a strategic provocation, a way of forcing the conversation beyond incremental optimization. A reminder that intelligence, once decoupled from biology, will always seek new substrates. Just as talk of Mars colonization reshapes thinking about sustainability on Earth, talk of space-based data centers pressures us to confront the real limits of our current systems. The transition from AI to AGI and eventually ASI will not be constrained by clever algorithms alone. It will be constrained by energy, heat, materials, and governance. Space may one day host significant computation, but only after profound breakthroughs in material science, autonomous maintenance, energy storage, and orbital infrastructure. Until then, the future of intelligence will be decided far closer to home. In the end, the most important question is not whether we can put data centers in space. It is whether we can build intelligent systems that coexist responsibly with the planet that created them. Space is a tempting escape hatch. Earth is a harder, more meaningful challenge. And that challenge, more than any orbital ambition, will define the path from artificial intelligence to artificial general intelligence, and eventually to artificial superintelligence.